Hello everyone. Today I am Rishabh Bhardwaj, Assistant Professor in Mechanical Department, taking the lecture of heat transfer. In this, today we will discuss about extended surface fins. Let's start with what is extended surface fins. As we know, in many engineering situations, means are often sought to improve heat dissipation from the surface to its surroundings. Whenever the available surface is found inadequate to transfer the required quantity of heat with available temperature drop and convective heat surface coefficient, extended surface and fins are used. Let initially started with what are fins. The fins are basically extended surface. They are used to increase the heat transfer rate from a surface to the adjoining fluid. The rate of heat transfer increases as the effective surface area of the surface increases with the attachment of fins. Then, how does the heat transfer takes place from a fin? As the heat transfer takes place from the fin by adjoining fluid by conduction and the convection. Next, we will study about the method to increase the heat transfer rate. We have the three methods by which we can increase the heat transfer rate, that are by increasing the surface area in contact with air or providing fins, by increasing the heat transfer coefficient for the surface. Third, by the increasing the temperature of the hot surface or decreasing the temperature difference between the hot and cold bodies. By by three these by the by three these steps we can able to increase the heat transfer rate. Let's discuss the working principle of the extended surface fins. In many engineering applications, the working or the principle of extended surface has been used. Large quantities of heat have to be dissipated from small areas. The fin increases the effective area of the surface, thereby increasing the heat transfer by convection. In other words, the shape of fins must be optimized such that the heat transfer density is maximized when the surface and the material used for the fins are constraints. Let's see the types of design or the types of fins. Generally, the fins are designed and manufactured in many shapes and forms. They manufactured in different geometries depending upon the practical application. The ribs attached along the path of the tubes are called longitudinal fins. The concentric and annular disc around the tube are termed as circular or annual fins. Pin fins and spines are rods protruding from the surface. As you can see in this figure, we have the several types of fins. In the first, it is the figure of straight fin of uniform cross section. Straight fin means a fin is extended straight and in a uniform motion. by which there is no deflection in the shape of fin. Second, we have a straight fin of non-uniform cross-section area, by which the fin shaped is transducing or changing or variable time to time or distance to distance. Third, we have a annular fin, in which a cylindrical rod having a plate surface which are extended some by the radius. Then we have a pin fin. Pin fin is kind of a small spike type fin. Let's discuss the next: temperature distribution and heat transfer rate for fins. First, we have the convection heat transfer, in which the temperature distribution and the fin heat transfer rate are much higher than the temperature distribution. In the second, we have a adiabatic condition, in which the values of pin heat transfer rate is the coefficient of heat transferring rate per unit. The constant temperature, where the temperature is being constant, then the values will remain the same. For the infinite fin length, the values could be the exponential values in the temperature distribution, but in the fin heat transfer, that will be the HPA and the theta. Let's discuss about the pin performance. The pin performance can be described in three different ways. The first is fin effectiveness. It is the ratio of fin heat transfer rate to the heat transfer rate of the object if it had no fins. The formula for this is Q final upon HA of collar body and theta B, that is the effectiveness of the fin, where ACB is the fin cross section area at the base. Then we have a fin performance can also be characterized by fin efficiency. This is the ratio of fin heat transfer to the heat transfer rate of the fin if the entire fin were at the base temperature. Then the efficiency that will be the QF by HAF theta B, where AF in the equation is equal to the surface area of the fin, and fin efficiency will also be less than 1. And the third one is the fin performance can be described is with all over the surface efficiency. That could be the QT by HAT theta B, where AT is the total area and the QT is the sum of the heat transfer rate of all the fins. Next, if we take the if we have to derive the expression for the one-dimensional differential equation of temperature for fin of uniform cross-section area, then initially we have to take some assumptions. That assumption could be the steady state heat conduction along the x-axis. Then the no heat generation in the fin. We have to assume that there is no heat generated in the fin. Third, we have the uniform heat transfer coefficient over the entire surface of the fin. uniform heat transfer coefficient over the entire surface of the fin. The material of the fin is homogeneous and isotropic. The fin and base material has no contact resistance. Then negligible radiation form from the fin, and the fin temperature at base uniform, that will be the T naught. You can see easily in this diagram that one base, that is the T naught, have one extended fin where we have taken small portion of body, that will be the heat is entering in the fin, that is the Qx, and the final output, that the Qx plus Tx, where heat can be convected. The small portion that could be taken, that will be taken as the dx, and the overall length of the fin, that could be taken as L, and the thickness of the plate or fin will be taken as the small t, and the temperature of the surroundings, that will be taken as the T infinity, and the base or the length of the fin will be taken as the B. Now consider in the elemental cross section dx, thick at distance x from the base of the fin. On the basis of heat balance for this element, the conduction heat entering at x is equal to the conduction heat leaving at x plus dx plus heat leaving by convection. That will be the Qx is equal to Qx plus dx plus Q convection. But the heat leaving at x is Qx is equal to minus Ka curl T by curl x, and the heat leaving at x plus dx is Qx plus dx is equal to minus Ka curl T by curl x plus curl Qx plus curl x. And the minus Ka curl x plus curl Qx by curl x, we will putting the value of Qx in this integral part. Then the equation that will be formed is, that will be that K is equal to minus K curl T by curl x minus Ka double differentiation of the temperature with respect to the square of the distance into dx. Also convection heat transfer is Q convection, that is H P into dx into the change of temperature with minus surroundings, where P is the perimeter and T alpha, that will be the temperature of surroundings. And now substituting the value of Ka curl square T by curl x square into dx minus Hp dx into T minus T alpha is equal to 0. Putting the value and simplifying this as curl square T by curl x square minus m square T minus T alpha is equal to 0, where m square is equal to Hp by Ka. Now take theta is equal to T minus T alpha, that will be the curl square theta by curl x square is equal to curl square T by curl x square. Now the equation becomes that curl square theta by curl x square minus m square theta is equal to 0. This is the differential equation of second order, which has a solution theta is equal to C1 exponential power minus mx plus C2 exponential power mx. The two boundary conditions are required by solving C1 and C2. Now, what are the advantages and disadvantages of effective fin area, surface area? Let's discuss about advantages first. By using the fins, heat transfer rate can be increased without any prevention maintenance. It is the cheapest way for increasing the heat transferring rate from hot bodies. And the disadvantages of this, that we know that the length of the fin is directly proportional to the heat transferring rate, but the large length is made to cause of bending in the fin and also increases the weight of the engine. Therefore, the overall efficiency will goes to decreases. Let's see, we have applications of extended surface fins. Common application of fin surface are with cooling of electronic components. Then we have a condensers and economizers of thermal power plant. Third, we have dry type cooling tower. Then air cooled cylinder of compressor, IC engines, evaporator and condensers of refrigerations and air conditioning system. It also being used in electric motor for rejecting the heat to the surroundings, and it has been also used in the transformers. If we see in the diagrams the uses in real life, and in the first, this is the straight fins. You have seen this component in the motherboard of the CPU in the desktop. This is the heat sink which is mounted over the processor, by which the heat of the processor has been rejected by the straight fins. Then we have a trapezoidal fins. This is the another way or the another type of fins by which the heat is rejected by the system. This component is also being used in the electronic parts. Then third one is annular fins. The annular fins are mounted over the central part, by which the angular fins are attached in a circular way, by which it can gain and cover the surface larger as compared to the straight fins, as much as the air trapped from the surroundings and the area covered by the fins will increase the heat transfer rate, by which the heating process is much higher than the other ones. Next, we have a sublines. Sublines. These are supplying fins are generally used in the motors, in several types of motor like a compressor, compressor, condenser, and many more, by which the supply transfer the heat to the surroundings as easy as possible, as it contain less space, but the effectiveness and the angles of these fins may provide the higher heat rejection rate as compared to the other ones. These are the compact and the effective devices or a type of fins by which the heat is rejected. So students, today in this lecture we have studied about the effectiveness of extended surface fins, by which we are able to understand that extension of any part and make it and allow them to cool in the surroundings will make the heat transfer rate high, and we are able to transfer the total heat of the system to the surroundings as much as easy and in a convenient way, by not making so much expensive condenser or any other devices installed in the parts. Thank you for watching this video and stay tuned for the next one. Thank you.